Okay. Hi everyone. Hi. So, is there any question? No. So this is the last session for lecturing. In the next week, we'll have presentation. Yes. And as I have said, you don't need to finish your project, but do the majority of your work, and prepare some results and as much as you can. And please present everything that you have in the presentation, and we will give you feedback, and then you will have about 10 days to apply the feedback and finalize everything and submit the report and code. So yes, I will make announcement for details of presentation and etc. in the course link. So that's one thing. Let's start this session. So here now we are gonna start factor analysis, probabilistic PCA, and variational inference. So last week, at the end of the last week, people got tired. So I talked about a bit philosophy, but philosophy of Bayes rule. But anyways, let's go to the mathematics. So consider a data set of n data points x1 to xn, then assume that every data point xi is generated from a latent variable zi. So I drew this figure. And I was saying that consider this figure. So we have xi, we have a latent variable or hidden variable zi, where xi is caused by zi or xi is conditioned on zi. And we saw that in the world, in the real world life, in metaphysics, we see this a lot. And I said that I don't mean supernatural, I mean metaphysics. Metaphysics includes supernatural plus a lot of other things. So I said everything that we see in this world might have some latent reason, right? Not necessarily supernatural, but there might be some latent reason that we can't see. And as we know, mathematics is modeling life. So we see this a lot in variational inference and probabilistic analysis. So as the dimensionality of zi and xi might differ, right? And I said the latent variable has a prior distribution, P of zi. And according to the Bayes rule, we have this equation 1, where this is posterior, this is likelihood or class conditional, this is prior of zi, this is prior on xi. And as we can write prior as a marginalized probability, we also call it marginalization. Anyways, and I said the proof of Bayes is very simple, because in the numerator, this is the joint probability of xi and zi, and this times this becomes the joint probability of zi and xi. We know that the order of variables in the joint probability doesn't matter. So this proves the Bayes rule. And then we said let pzi be an arbitrary distribution denoted by qzi. Okay, so I renamed the distribution to be qzi. Suppose the parameter of the conditional distribution of zi on xi be theta. So theta is the parameters of this distribution. Every distribution has some parameters. For example, Gaussian distribution has mean and variance, right? Something like that. Hence, P of zi given xi, we can write it as P of zi given xi and theta. Note that in probability, sometimes we write theta as a, for example, assume I have this distribution and it has some parameters. Okay, people write it in two ways. Either they write it with semicolon, or they write it as this, given theta. What is the difference between these two? The first one means that theta is just a parameter, but it is deterministic. Okay. The second one assumes that the parameters of the distribution is a random variable. Both almost have the same meaning, so you can use them interchangeably. You see that interchangeably a lot. You can assume that the parameter of distribution is a random variable and you condition on it, or you can assume that this is just a parameter. Okay. Anyways, so here we are assuming that theta is a random variable, right? And we are conditioning on that. And according to the Bayes rule, again, we can write it in this way. So far clear? Please interrupt me whenever you have any question, okay? Because I think this session is a bit a dense session. Okay, so consider a KL divergence or Kullback-Leibler divergence. What is that? This is a divergence or difference. This is one of the measures for difference of two distributions, right? When two distributions are equal to each other, it means that all of their moments match, right? What is moment of the distribution? You know, so expectation of x is the first moment. Expectation of x squared is the second moment. Expectation of x cubed is a third moment, etc. So we have infinite number of moments for every distribution. And what is the first moment? That's the mean of distribution. What is the second moment? That's related to both mean and variance. Recall the formula of variance. I think it was, if I'm not wrong, expectation of x squared minus expectation of x squared, right? As a result, it has relation to both variance and mean. What is expectation? What is the third moment? It's related to the skewness of the distribution. What do I mean? Whether the distribution is like this or like this, skewed, okay? Again, fourth moment, we have a lot of moments. So each moment shows some kind of characteristic, some characteristic of the distribution. And every distribution has infinite number of moments. When the moments of the two distributions, all of them match, it means that they are equal to each other. So there are several ways to calculate the difference of two distributions. One of them is maximum mean discrepancy, MMD, maximum mean discrepancy, okay? That's related to kernels. So its idea is this. Its idea is simple. When you want to see the difference of two distributions, you need to calculate the difference of each their moments, right? The first moments, how different they are. The second moment, the third moment. Of course, I think the initial moments are more important. So mean is more important than variance, then the skewness, etc. Okay, so you need to calculate the difference of all of the moments, right? But you have infinite number of moments. It's infeasible to do that. Then maximum mean discrepancy says that let's map this distribution to the Hilbert space or feature space, right? Recall the kernel SVM lecture for feature space. We map them to the feature space or reproducing kernel Hilbert space. Then we use simple Euclidean distance between them in the feature space. That distance is a good estimate for the difference of all of the moments in the input space, right? As you see, it uses kernel. This is called maximum mean discrepancy, or MMD, proposed by Sholkov et al. In Max Planck Institute, the god of kernels, right? Another measurement to measure the difference of two distributions is KL divergence, proposed by Kullback and Leibler, okay? And this is not a distance metric because it's not symmetric. One of the properties of a distance metric is that it needs to be symmetric, right? But this is not symmetric. KL of P and Q is different from KL of Q and P. We have one measurement based on KL divergence, which is symmetric. I think its name was Johnson something divergence. If you Google Johnson divergence, it comes, okay? So what is that? It basically says that KL of P and Q plus KL of Q and P divided by 2. Then it becomes symmetric, am I right? So KL of P and Q plus KL of Q and P over 2, okay? Anyways, so, and KL divergence, when it is 0, if and only if, so it's two-sided. The two distributions are equal. The greater the KL divergence becomes, the more difference they have, okay? But there is no upper bound on KL divergence. That's one of the issues with KL divergence, okay? So consider this QZI and P of ZI given XI. Always have this probabilistic graphical model in mind. So this is called probabilistic graphical model because we model it by graphic, right? So XI is conditional on ZI. Then here we say Q of ZI, the prior of ZI, the distribution of it, and P of ZI given XI. Okay, given XI. So these two, I want them to be similar to each other, right? I want them to be similar. And this is according to the definition of KL divergence. continuous scale divergence. Okay, and then I logarithm of a over b, I write it as logarithm of a minus logarithm of b. So I can simplify to these two. Okay, so far clear? Are you listening to me? Because you're not looking at it. Okay, and then what are we doing? Let me think. Equation 2. I'm using Bayes rule now. So here I have probability, I have probability of zi here, given xi and theta, but rather than this, I use this Bayes rule, the right-hand side. So I have 3 parts, right? Inside the logarithm. As a result, it becomes these 3. Okay? And then what do we do? Probability of xi given theta, which is this logarithm of probability of xi given theta, is not dependent on zi, right? Doesn't have z. So it can come out of the logarithm, right? So it comes out of the logarithm. It becomes this times integral of dzi over all range. The integral of dzi over all range becomes 1. Okay? And the rest is remains inside the integral. So far clear? Okay. Then I recap all of the logarithms again to each other. So logarithm of a over b is logarithm of a minus b, right? So logarithm of a minus b, I write it as logarithm of a over b. Okay, so it becomes like this. Then so what is this? I can write it by chain rule in probability. Write it as this: probability of xi and zi given theta. Okay, am I right? What is chain rule in probability? Don't know that? So I have p of xi given zi. Forget theta for now. P of zi. Do you agree that this becomes probability of xi and zi? Now condition it on theta as well. Okay, so this becomes this. And what is this? Interestingly, this is a definition of Kähler divergence again. So I can write it as Kähler divergence of this. Okay, so we simplified this to this. And now I rearrange the terms. So I bring this to the other side of the equation. Consider this left-hand side equals to this right-hand side, and the rearrange the terms. So you will get equation 3. Am I right? Okay. So we have this. We have this. And now we define something named evidence lower bound, or ELBO in short. One of the most important things in probabilistic machine learning. Okay. ELBO. What is that? It's defined as this: minus Kähler divergence of prior of zi and probability of xi and zi given theta. Okay, this is, and we will see why it is lower bound, why it is called lower bound, and we'll see that in a few seconds. Okay, so now replace this. Am I right? If I'm not wrong, yes. Replace this is with what we just defined, with the ELBO. So it becomes, sorry, this, it has minus in it too, because the ELBO definition has minus in it too here. So this, replace it with this evidence lower bound. So we'll get this. Now again, rearrange the terms. So bring this to the other side of the equation. You will get this equation 5, right? So far clear? Now we know that one of the properties of Kähler divergence is that it's greater than or equal to 0, right? Right? Because when the two distributions match completely, it's 0. Otherwise, it's greater than 0, right? So this term without the minus behind it is greater than or equal to 0. As a result, what does it mean? This is less than or equal to this part. Equation 6, right? I just proved that this, which we named it ELBO, is a lower bound for probability of xi given theta, or logarithm of probability of xi given theta. And what is probability of xi given theta? That's the likelihood of data. Xi is data, right? So, or log likelihood of data, doesn't matter. Yes. So, did you understand equation 5? So now, this part is non-negative. Do you agree? So I have this logarithm minus something non-negative. As a result, this is either equal to this logarithm or less than it. Less than it. Equation 6. Okay. Now this means lower bound, right? This L is always less than or equal to logarithm of P. So it's a lower bound. So if logarithm of P is like this L is always like this, right? It's always below it or equal to it. So it's lower bound, right? Lower, and what is this right-hand side? This is the log likelihood of data, right? So it's a lower bound for log likelihood of data or likelihood of data, right? That's why it's called lower bound, evidence lower bound. Okay, so far clear? Now, this probability of xi given theta, which I named the likelihood, this is also called evidence. Now you understand why it's called evidence lower bound, because this is a lower bound for evidence, okay? And now this lower bound, when does it get tight? What do I mean by tight? So this is also a lower bound. This is also a lower bound. Both are lower bound, but this is a tight lower bound. A tight lower bound is a better estimation, right? So when does it, we want it to be a tight lower bound. When does it get tight? When this equals this, right? As a result, the scale divergence, this scale divergence should become almost zero, right? So when does this become always zero, almost zero? When these two distributions are almost equal to each other. When these two, so when this happens, when does it mean? When these two are equal to each other. So basically, I want these two to be almost equal to each other. As a result, this scale divergence, which was greater than or equal to 0, should be set to 0. So it's sandwiched between 0 and 0. As a result, it needs to be 0. So these two distributions need to be equal to each other. So far clear? Okay, now let's continue. What did we found? So this is what we had, right? The formula that we had in the previous slide. Okay, now let's visualize it within the figure. So what is this? Let this part be the evidence, log evidence or log likelihood of data, okay? Which is this part, the left-hand side of this formula, right? According to this formula, it is equal to this plus this, right? What is this? So let this lower bound be denoted by here. As a result, this is elbow, so assume this is 0. This is elbow here. And we'll also have, this is this scale divergence, right? These two, if we sum them, it becomes the left-hand side, which is the log likelihood. So far clear? Do you understand this figure? Okay, let's continue. Now, according to the maximum likelihood estimation, what is it? So we have some parameter and we want to maximize the log likelihood or likelihood of data, right? With respect to that parameter. This is called maximum likelihood estimation. We already talked about it previously in this course, right? Now, according to MLE or maximum likelihood estimation, we want to maximize the log likelihood of data, right? So according to equation 6, do you remember equation 6? It was this. I'm repeating it here. What is this? This is exactly the lower bound for log likelihood of data. Maximizing this elbow will also maximize the log likelihood. Do you agree? So rather than maximizing the log likelihood, do you agree that I can maximize its lower bound? When you maximize the lower bound, the function itself is also maximized. This is one of the techniques used a lot in optimization. Assume you have a hard objective function, hard to maximize. Rather than maximizing that, you can find a lower bound for it and maximize the lower bound. When you maximize the lower bound, you also are maximizing the function, assuming that the lower bound and the function have some kind of shared parameters, right? Agree? Variables. So that's a technique. As a result, this equation holds for any prior distribution Q, right? For any, did we have any assumption on the Q? No. We want to find the best distribution to maximize this lower bound. Which Q maximizes that, right? This lower bound. As a result, we use expectation maximization for variational inference. And what was expectation maximization? Recall a few lectures ago where we talked about expectation maximization and Gaussian mixture model, right? Do you remember that? We said in maximum likelihood estimation, we assume that everything is known, but what if we have some missing data? Then we said, let's replace the missing data with the expectation of missing data with respect to the available data. So everything will be known. Then we maximize the expected likelihood, right? And we do it iteratively until convergence. This is called expectation maximization. So expectation maximization is nothing but maximum likelihood estimation, but we are replacing the missing data with the expected missing data, right? And as it is, it has two steps. We need to do it iteratively because it is kind of an alternating optimization until convergence of them, right? So we have E step, which is expectation step, and M step, which is maximization step, right? So what do we have here? So Q and theta, we have two things, right? Q max, so argmax of this lower bound with respect to Q gives us Q, and then we put this QT inside the lower bound, then we maximize this lower bound with respect to theta. So as you see, Q and theta are changed alternatively in the iterations until they converge. They both converge and they don't change significantly, right? T here denotes the iteration index, right? So E step in the expectation maximization for variational invariance. Let's talk about the E step first, and then we will also talk about M step, okay? E step, what was that? Maximize the lower bound, right? Rather than maximizing the likelihood, we said let's maximize the lower bound. Maximize the lower bound with respect to Q. We just saw that here. It was here, right? Equation 8. So now let's see. Let's use equation 5. What was that? This. So for lower bound, we have equation 4. We also have equation 5, right? So let's use equation 5 now. So it has these two parts, right? Have a mental picture of this. Let's go to that slide again. So it had two parts, right? Maximize of F plus G. You can write it as maximize of F plus maximize G, right? This is exactly what we are doing. And then, so I'm repeating the first term as before, maximize minus something. It's equivalent to minimize it. So minimize it without negative sign, okay, with respect to Q. So far clear? Okay, now the second term, which appears here, is always non-negative because it's a KL divergence, right? So its minimum is 0. We are minimizing this. Its minimum is 0, right? So we set it to 0. I'm solving this part here. Now, minimize something which is non-negative without any constraint. So its minimum is 0. Set it to 0. As a result, these two should be equal to each other because KL divergence of two distributions is 0 if and only if they are equal to each other. It's a two-sided thing, right? So they are equal to each other. And what is this? This is exactly what we talked about in equation 7 for being tight. Do you remember? Tight lower bound. So the E step, as a result, replaces Q of Zi with probability of Zi given Xi and theta, right? To satisfy this equation. So this is E step. In this figure, what happens? Let's analyze this equation in this figure. So this is the KL divergence, right? This is the KL divergence. When you do this KL divergence becomes almost 0. As a result, it means that push this elbow upwards. So this lower bound becomes tight. Okay. Now M step in the expectation maximization for variational invariance. What is that? What is it? So basically it says that maximize the lower bound with respect to theta this time. Agreed? Agreed. So now I'm using equation 4 this time rather than equation 5. What was equation 4 for lower bound? It was this one, right? The definition of lower bound, the definition of lower bound, elbow. So I'm putting this here, right? It has negative in it, negative KL divergence. So now what do we have? I'm replacing KL divergence with its definition. Integral, right? It has some definition. Just Google KL divergence and you'll see this formula, okay? And then what do we do? So I have logarithm of A over B. I write it as logarithm of A minus logarithm of B. Okay, so I break it down into two parts. Agreed? Also note this, there is minus here. So I have noticed that minus behind the integral as well. Then let's talk about the second term, right? The second term, do you agree it's constant with respect to theta? Do you see any theta here? Okay, as a result, what happens? What happens? You tell me. So you can ignore it, right? You can ignore it because it doesn't have any parameter theta in it. So I can ignore it. Okay, so this side, which is this, equals this side. Maximum of this with respect to theta. Agree? Note that, why can I ignore it? What? You can you be loud? Like, no, you're saying that it's constant, right, with respect to theta, right? But I'm saying that what? Okay, let me tell you this. I think this is important for optimization. I have said it, I think, in this course once. Assume I have maximized f of theta plus g of lambda with respect to theta, where g is not a function of theta at all. Okay, can I drop g of lambda? Yes, but there is some but. If so, you drop it, it becomes maximize f of theta with respect to theta, and you solve it. Assume you find theta, right? If only argmax of this was important for you, you are done. You already found this set. But what if the maximum is important to you, the maximum function? Then you have to put it back in the original thing. F of theta star plus g of lambda. G of lambda in the maximum is important. You have the maximum plus some constant, right? But if argmax is important to you, you're done. You don't need that, right? So you should be careful about it. Here, argmax is important to us. Theta, right? In the MS step of expectation maximization, recall that. Recall this equation 9. Argmax is important to you. Agreed? Okay, so that's one thing that you should notice. And now, so I drop this as I explained. This becomes equal to this, right? Ignoring the second term. Then you tell me, what is this? Interestingly, this is the definition of expectation. Continuous expectation, right? With respect to Q. This is the probability, and this is a function, right? This is expectation of f of x, for example. F of some random variable. And then, as a result, the M step becomes this. And as it is argmax, I don't care about the dropped part at all, right? Okay, so M step is also explained. This is what we found. I'm repeating it here. Now let's analyze it in the figure. In the figure. So where was that? So this probability of xi and zi, what does it mean? Would you take the expectation with respect to q of zi? So basically, this part, this log is kind of the log likelihood, logarithm of probability of xi. This is probability of xi and zi, but you're taking expectation with respect to q of zi. So it's kind of probability of xi. As a result, you're pushing this line above because you're maximizing it. Okay, now consider the E step and M step together in this figure. What was E step doing? It was pushing the elbow above, right? Right? Do you remember? Yeah, so when I say pushing above, it means maximizing it, right? This was E step. This was M step, which we just saw. Do you see what are they doing? E step is pushing elbow toward likelihood. M step is pushing likelihood above. So it's like two people who are playing a game. E step is person one, M step is person two. E step comes to catch M step, but M step goes away. So there's game. You can see, analyze it as a game theory too, right? So it's a game between these two, but finally E step catches M step because their distance becomes smaller and smaller. That's the convergence in expectation maximization. So E step moves, M step also moves, but their distance becomes smaller until E step, the elbow becomes very tight. And that's the convergence of expectation maximization algorithm. Right? Interesting. And if you put the two steps together, this is an EM expectation maximization, E step equation 12, M step equation 13. We do it iteratively until convergence. Interesting. This is called variational inference. In variational inference, sometimes the parameter theta is absorbed into the latent variable zi. Okay, so you can consider zi and theta together as one latent variable. Sometimes they do that in the literature. So for example, probability of xi and zi and theta, according to the chain rule, do you agree? According to the chain rule in probability, is probability of xi given zi and theta times probability of zi given theta times probability of theta. Now I take these two as one probability term. Then zi theta is absorbed into zi. Therefore, this becomes this, right? Sometimes they do that in the literature, okay? So we talked about variational inference. Any questions so far? No? Now factor analysis, which uses variational inference, okay? Factor analysis, it's a very old and fundamental generative model. It is one of the simplest and most fundamental generative models. What is generative model in machine learning? It's obvious from its name. What is it doing? Generative model. It generates this data, generates something, okay? But out of what? The beauty is that it usually generates data out of noise. Okay, the latent variable usually is noise. So basically, you have a noise distribution. You sample noise from distribution, you feed it to the generative model, it generates some real world data. Okay, but it needs training, of course. After training, I mean. So assume. So basically, it's kind of corresponds every noise to some real data. In other words, assume we train some generative model for this class, Then, for example, my noise is one-dimensional Gaussian distribution. Assume, okay? Then maybe you are sampling from this distribution. Assume you sample from here. It gives you some. So with this probability, it gives you this zi. You feed it to the generative model, it outputs Benjamin. Okay. You go a bit further, you sample this zi, you feed it, and it gives you U, for example. You do it again, it gives you another student. So basically, Benjamin is corresponding to this. Another person is corresponding to this. So everyone is corresponding to some part in the latent space. You see that? You see that? That's why in many generative models, they also make a grid for showing how it is working. They assume that their latent variable is 2D, two-dimensional. Then they move in this space. They move by fine steps. And they show the corresponding real-world data. Assume it is, this generative model is trained on digits with the two-dimensional latent variable. What happens? Then when they do that, after training, they show that probably digit 0 corresponds to the top left corner in the latent space. And then when you move, it becomes 1. In the top right, assume is 1. it depends on how it is trained. Okay, in the left, bottom left, it becomes maybe 9. By the way, user doesn't say that. The generative model finds it out itself by training. Yeah, so it assigns every zi to some xi, okay, by training, by optimization. And after training, you can analyze the latent space. And interestingly, you will see that every corner is corresponding to something, every part of the latent space. And this is semantically, it is semantic. What do I mean? When you move from this corner to this corner, you will see the transition from 0 to 1. How does this happen? For example, this is 0, becomes narrower, 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 becomes 1. Interesting. For example, it is moving up. When you move, assume here is 9. 0 becomes a bit like this, then this, then this, then this, right? 9. You can see the transition, the smooth transition, and that's very cool, right? So these are generative models. There are a lot of generative models in machine learning. One of them is factor analysis. Okay, one of them is probabilistic PCA, which we'll see today. Another one is generative adversarial network, or GAN. Another one is variational autoencoder. Variational inference, which I explained to you right now, you can implement it as an autoencoder neural network. That's called variational autoencoder. It was proposed by Max Welling, one of the important scholars in machine learning. He's in Netherlands now, okay? And where were we? So these things. Another generative model is variational diffusion model, state-of-the-art generative models nowadays. Okay, so we have a lot of things. Now I'm going to talk about factor analysis, one of the very old and most fundamental generative models. Factor analysis assumes that every data point xi, which is d-dimensional, is generated from a latent variable zi, which is p-dimensional. Okay. The latent variable is also referred to as latent factor. Okay. Hence the name factor analysis. Okay. In the factor analysis, we assume that the data point xi is obtained through the following steps. Okay. Please focus on what I'm saying. So first, linear projection of the p-dimensional zi. So zi is p-dimensional, the noise. Xi is d-dimensional. Okay. So we'll do linear projection of zi, recall preliminaries. I talked about linear projection onto a d-dimensional space by some projection matrix, lambda. Okay. D by p. Then applying the linear translation. Linear translation means translation plus some bias, right? Vector bias, of course. And finally, adding a Gaussian noise, which is also this noise. This Gaussian is a vector, noise vector. Okay. And with Gaussian, with covariance matrix, what was it called in Greek? It was psi, I guess. Psi, with psi. Okay, which is d by d, because the noise is d-dimensional, so its covariance matrix is d by d. Okay. As the noises in different dimensions are independent, okay, they are assumed to be independent. Okay, the covariance matrix psi is diagonal. Okay, it's a diagonal covariance matrix because the noises are independent from each other. Then now let's show the factor analysis as a probabilistic graphical model, PGM. Okay, so here it is. As you see, I have latent variable zi, it causes xi, and then I have noise epsilon, which is a Gaussian distribution with mean 0 and covariance psi. Why should the mean be 0, the mean of the noise? Because when this is an additive noise, and when I add the noise to the data, I don't want to change the mean of data. So when the data is here, I want to be around it. If the noise has a mean itself, rather than being here, I will be here, around here. This is the mean of the noise, right? That's one thing. Yes. What a visible. So this is visible data, xi, and zi is a latent factor, right? for simplicity, the prior distribution of the latent variable can be assumed to be a multivariate Gaussian distribution. For simplicity, we assume that, okay? So prior of Zi, the latent factor, let it be a Gaussian distribution. Zi given mu, so its mean is mu0 and its covariance is sigma 0, okay? Then what happens? By the way, what is I? What is the subscript I? It's the ith point. Xi is the ith data point. Each data point has its own latent factor, right? Okay. And mu0 is mean p dimensional, sigma 0 is the covariance p by p, right? Z, and this is determinant of the matrix. This is the PDF of the multivariate Gaussian distribution, right? Probability density function. Xi is obtained through through these things. Do you remember I said linear projection of Zi by lambda? So I think I have written it here. Yes. Do you agree that this is linear projection? You might say, no, this was linear projection, right? Now I define U transpose as lambda. Does it matter? No. So lambda Zi is also linear projection. U transpose Zi is a linear projection onto the column space of U. Lambda Zi is a linear projection onto the row space of lambda. Okay. Okay, that's one thing. For column space and row space, recall preliminaries of this course, right? And then we apply some linear translation. As you see, after this linear projection, I add mu, some linear translation, the vector. And then we add a Gaussian noise with covariance psi. As you see, I'm adding the noise else. So I just described equation 19. Okay. So the data point xi has a conditional multivariate Gaussian distribution given the latent variable. Okay. So probability of xi given zi becomes what? A Gaussian distribution. Why? Because the noise was a Gaussian distribution. Okay. And as you see, the covariance of this Gaussian distribution is the covariance of noise, psi. And the mean of this conditional distribution is what? Lambda Zi plus mu, right? Because this is exactly the mean. But the covariance comes from the noise, right? And this mu is the mean of data. By the way, why is this linear translation required plus mu? And why is it mu? Mu is the mean of data. Why does it make sense to add mu, nothing else? Let's take expectation from the sides of this equation. Expectation of xi, I mean the mean, right, is expectation of lambda Zi. We know that expectation is a linear operator. So plus expectation of mu plus expectation of epsilon. What is expectation of lambda Zi? According to equation 20, Zi, the prior of Zi, I think I already explained this. The prior of Zi, we assume that, here I have said it. We assume that mean is 0, its mean is 0, and its sigma is 1. So here, basically in equation 14, for simplicity, I assume that mean of Zi is 0, and mean of the covariance of Zi is identity matrix. Okay. Okay. So far clear? So far, are you coming with me? So as a result, what happens to this? This expectation becomes 0, because expectation of lambda Zi becomes lambda expectation of Zi, and expectation of Zi is 0, right? What about expectation of epsilon? According to equation 21, this is also 0. What is expectation of mu I? Mu I is not random variable. It becomes mu. Expectation of xi is mu, as expected, right? Because expectation of xi is the mean of xi, and the mean of xi is mu. That's why this linear translation is required to have the mean of data. And this needs to be the mean of data, okay? Again, I'm assuming that the prior of the latent factor is a standard Gaussian distribution, okay? And the prior of the noise is has mean 0, but covariance psi. So far clear? Here, let's talk about the marginal distribution of xi. Probability of xi. So the marginalization, do you remember? Recall preliminaries. I can say probability of xi given zi times probability of zi, because this, according to the chain rule, is joint probability of xi and zi. But I integrate it with respect to zi. So it becomes probability of xi, right? This is marginalization in probability, right? And then, so now also add the parameters in this equation. I can do that, okay? Because these are the parameters of the distribution, these distributions. Okay. Then, do you remember I said that you can say probability of x semicolon theta or given theta because of that, okay? And now, give me a second to remember. Okay. This step A is because mean is linear and variance is quadratic, so the mean and variance of projection are applied linearly and quadratically respectively. What do I mean? Because when you have x, assume you project it by lambda x, what happens to mu? Becomes lambda mu. Mean is linear. What happens to the covariance? Let's call it sigma, whatever. It becomes lambda sigma lambda transpose, right? It's quadratic. Why is it lambda sigma lambda transpose? Because I assumed lambda is u transpose. If it was x maps to u transpose x, then sigma would map to u transpose sigma u. But here, as I'm projecting onto the row space, it becomes lambda sigma lambda transpose. Okay. So as a result, I have, according to this, I have this linear projection. So I have this. Okay. Also, my covariance becomes psi plus this, what I just talked about, right? But as I said, for simplicity, I assume that mu 0 is 0 and sigma 0 is I. Then this becomes simplified. Okay. This becomes simplified. But in general case, when I have mu 0 and sigma 0, I can define the whole thing as mu hat. Also define the whole thing here. So also define this to have this. What do I mean? Let me tell you. So lambda sigma 0 lambda transpose. By the way, if you are finding this topic hard, this is one of the hardest topics in probabilistic machine learning. Is hard. Okay. So it's not my fault. It's hard. Okay. So what is this? Do you agree that I can write it as lambda sigma to the power of half, sigma to the power of half lambda transpose? Do you agree? Am I allowed to do this? Yes. Why? Only I'm allowed to do this if all of the elements of sigma 0 are non-negative, right? But they are non-negative because this is covariance matrix, right? So covariance matrix is non-negative. Covariance values are non-negative. So I'm allowed to do this. Then I'm defining this as lambda hat. As a result, this becomes lambda hat transpose, which is here, right? So this is general case. But if we assume these things, for simplicity, they become simpler. Okay. And we'll have these things. So far clear? Okay. Now the joint distribution of xi and zi. But so assume yi, I define it to be concatenation of xi and zi. Xi is a data, zi is a latent factor. This is also a Gaussian distribution because everything here was Gaussian. So the concatenation is also, the joint distribution is a Gaussian distribution with mean mu y and covariance sigma y. Okay. Now, what was expectation of xi? I already talked about it. It's this. Expectation is a linear operator, so it becomes lambda expectation of zi plus mu. Mu is a not random variable, and also expectation of epsilon. So this is 0, this is 0, so it becomes mu as expected. Okay, we already talked about it. As a result, the mean mu y, because of this, is mu x, concatenation of mu x and mu z, right? And we just saw that mu x is mu, but mu z is 0, according to our assumption. Okay, so far clear? As you see, I'm going step by step. Okay, so there is a lemma. We accept this lemma without proof. Okay, there's a formula. Okay, consider two random variables, xi and zi, with different dimensionalities, not necessarily the same dimensionality. Okay, so the concatenation yi is d plus p dimensional. Okay, assume that xi and zi are jointly multivariate Gaussian. Okay, hence the variable yi has a multivariate Gaussian distribution, right? Okay, then what is the mean and covariance? They can be decomposed because here I have decomposition. The mean and covariance can also be decomposed, okay, into these things. Mu y can be written as mu and mu 0, where mu and mu 0, mu is the mean of xi and mu 0 is the mean of zi. What about sigma? The covariance also is decomposed into 4 parts because the data is decomposed into 2 parts. Okay, sigma 1, 1, sigma 1, 2, sigma 2, 1, sigma 2, 2 with these dimensionalities. Okay, of course, sigma 1, 1 is d by d, sigma 2, 2 is p by p. The other ones are d by p or p by d. Okay, and the covariance notes the dimensionality of mean and covariance, right? Okay, so now also we have this. So by the way, for this lemma also you can see the reference 7. Okay, I'm giving you the reference. Okay, the conditional mean of x given z, mu of x given z. And what do I mean? The mean of distribution of conditional distribution of x given z is this. This is a formula in mathematics, in linear algebra, okay, which is d-dimensional. What about x given z? It is also d by d, because this is x given z, and x is d-dimensional. X given z, right? D-dimensional, so its covariance is d by d. This is also the formula, according to that decomposition that we have. Okay, I know I'm not providing the proof, but I'm giving you the reference. Okay, likewise, you can have z given x, the mean and covariance of z given x, but they become p-dimensional and p by p. Okay, so far clear? Now let's use these formulas. So what is sigma 1, 1? Sigma 1, 1 in our factor analysis is sigma x, because y was concatenation of x and then z, right? Sigma 1, 1 is sigma x is the covariance of prior of x. Okay, covariance of x itself. So what is the definition of covariance? Expectation of xi minus mu times expectation times xi minus mu transpose, right? Assuming that xi and mu are column vectors, right? So now let's replace xi with the formula of factor analysis. What was that? It was this. Equation 19, this one. Equation 19. So if we do that, it becomes this also here. I'm just substituting xi, the formula of factor analysis rather than xi. Okay, so what happens then? Now I multiply the terms to each other. We have a bunch of terms here, and also first I apply the transpose to the parentheses, and then I multiply the terms to each other. Right? I will get these terms. So far clear? Okay. Then I know expectation is a linear operator, so I can break it down. This, by the way, lambda is not random variable. It comes out of the expectation. Here also. But we know that both zi and epsilon are random variables. Okay. What is expectation of zi transpose? Do you agree that expectation of zi transpose equals expectation of zi minus mean of z times zi minus mean of z transpose? Yes, because mean of z was 0. And what is this? This is covariance of z. What was covariance of z? Identity. Identity matrix. Okay. What is this? Both of these are 0. The mean of z and the mean of noise. Both are 0. 0 times 0 is 0. Okay. Again, these are 0. So 0, 0 vector. What is this? Again, you can write it as expectation of epsilon minus mu of epsilon times expectation of, times epsilon minus mu of epsilon transpose, because mu of epsilon was 0. And what is this? This is covariance of epsilon. What was covariance of epsilon? It was psi. It was psi, right? So we just saw that sigma 1 becomes lambda transpose plus psi. I'm deriving the formulas of factor analysis for you. You see this formula in factor analysis. I'm deriving these for you, okay? Sigma 1, 2. What is that? It is sigma xz in factor analysis. I'm gonna use this formula. What is this? So covariance of 2 different random variables. This becomes expectation of xi minus mu, mean of x, times zi minus mean of z transpose. Mean of z in general, we denoted that by mu 0, but we assumed it is 0. So I replace it with 0. Okay. Xi, I also replace it with the formula of xi in factor analysis, right? So again, I apply this transpose on zi, and then I multiply the terms to each other, and I also know that expectation is a linear operator, so it breaks down. And also I know lambda is not random variable, comes out of expectation. These two are 0, go away. What is this? Again, according to this, it's the covariance of zi, and this is identity matrix, right? So it became lambda. Simple. It became very simple. Sigma 1, 2 became lambda. Okay. What about sigma 2, 1? Sigma 2, 1 is sigma 1, 2 transpose. So it's lambda transpose. What about sigma 2, 2? What is sigma 2, 2? This is sigma of z. What was sigma of z? The covariance of z. We assume this is identity matrix. So as a result, we have all of the sigmas. Let's put them together. We also calculated their mean. Let's put them. So we just found all of the parameters of the joint distribution of x and z in factor analysis. Right? Beautiful. Okay. What about marginal distribution of the data? Probability of xi. You can write it as probability of xi given its parameters. What is that? It's a normal distribution, Gaussian distribution, because everything is Gaussian, with mean mu and this covariance. Why? According to this joint, because when you marginalize for x, you will get its mean and only its this covariance, right? Agreed? This mean and this covariance. This is the reason. Okay, this is it. Now, just give me a second. according to the lemma that we had, equation 29 and 30, what was equation 29 and 30? These two. I'm going to use these two formulas for mu of z given x and covariance of z given x. Okay. The posterior or the conditional distribution of latent variable. So Q of Zi, according to equation 12, what was equation 12? I don't remember it. We should go back and see. I don't memorize them. Equation 12. This is the E step in expectation maximization of variational inference. What did we do in that E step? We said, let's copy probability of Zi given Xi to Q of Zi, right? As a result, I can write Q of Zi after convergence as probability of Zi given Xi, right? So far clear? So I raise this, okay? As a result, I can also have these parameters, I add them here, right? What is this? This is the condition, because of this is a Gaussian distribution with mean of Z given X and covariance of Z given X. So far clear? Now I'm gonna use these two formulas that we had in the lemma. I'm just replacing sigma 1, so do you remember this lemma? It had sigma 2, 1, sigma 1, 1, right? Sigma 2, 1, sigma 1, 1, sigma 1, 2. We just calculated all of these for factor analysis. Put these in the formula, okay? It gives you these two equations, 36 and 37, okay? And then recall that the conditional distribution of data given the latent variable, which was probability of Xi given Zi, was introduced in equation 15. What was that? I don't remember. You should go back. Don't memorize anything in your life. I'm telling you. Probability of Xi given Zi was this. It's the normal distribution of lambda Zi plus mu and psi, right? We talked about it. So Xi given Zi. This is exactly, I'm repeating it here, right? So I'm repeating equation 15 here. Now, if data are centered, what happens? Mu becomes 0, right? Then this becomes simplified. The probability of Xi given lambda and so this equation 34, this one becomes simplified to this. Mu becomes 0, right? If the data is centered. What do I mean by centered? Its mean is 0, right? And what about this one? Probability of Xi given Zi equation, this equation 15. This is also becomes simplified. This mean becomes 0, goes away. Right? Right. In some works, people center data as a pre-processing for factor analysis. And therefore they use these two equations, these equations. So you shouldn't be confused. If they center data as a pre-processing, and then it becomes more simplified. Do you remember? Why do they do that? Because they do it a lot in machine learning. In PCA, we have to center data. Do you remember? In probabilistic, in principal component analysis, PCA. But here we don't have to, but sometimes people do that as a pre-process. Okay. Now, so far we talked about the formulas. Now we can also find the parameters lambda and psi. Okay, using expectation maximization, using the variational inference. Okay. I don't explain the details of expectation maximization for factor analysis. Otherwise, I might overwhelm you. Okay. Please refer to our tutorial paper, Factor Analysis, Probabilistic Principal Component Analysis, Variational Inference, and Variational Autoencoder Tutorial and Survey. It's available in archive. For details of expectation maximization steps in factor analysis, let me briefly show you the steps. This is a tutorial. By the way, it has appeared as a chapter. It has been broken into 2 chapters in our book, to Elements of Dimensionality Reduction and Mindful Learning. If you go down, so you can see how complicated the steps are. Let me find it. Here it is. Section 3.5. Do you see? I'm doing the variational inference. These are all of the steps. I didn't want to overwhelm you, so I just refer you to this tutorial paper for if you want to know more details. For example, you see, this is a formula that we end up with. Okay, these are the formulas. Where were we? Okay. Now, factor analysis is over. Okay, over. Now let's talk about probabilistic PCA. We have talked about PCA, principal component analysis, in previous lectures. This is probabilistic PCA, probabilistic principal component analysis, and I will tell you how they are related to each other. Okay. Probabilistic PCA or PPCA was proposed in the years 1997 to 1999. Interestingly, it's a special case of factor analysis. Okay. How is it a special case? We set psi to be sigma squared I. What does it mean? Do you remember in factor analysis, we assumed that the noises are independent. So the covariance matrix becomes diagonal. But we didn't say that. We didn't say that then the variances of noise across different dimensions are the same. We said just it's diagonal. The diagonal elements of a covariance matrix of noise were not necessarily equal to each other. In probabilistic PCA, they are also equal to each other. Equal to sigma squared. What does it mean? When I say this, what does it mean? It is an isotropic noise. What does it mean? What is isotropic noise? It's like a hypersphere. It's not an oval. If you visualize the noise in the space, in 3D, it becomes a sphere. It doesn't become an oval or an ellipsoid. It doesn't become an ellipsoid or oval. It becomes like a sphere. In higher dimensions, this is a hypersphere. In all directions, its variance is the same. Okay. So as a result, the probability of this error, epsilon, becomes a Gaussian distribution with mean 0 and covariance sigma squared I, right? And its probabilistic graphical model is very similar to the graphical model of factor analysis, but the mean of the noise is 0. So because of having 0 covariance of noise between different dimensions, because this was the assumption of factor analysis itself, PPCA assumes that the data points are independent of each other given the latent variables. Okay. PPCA is a special case of factor analysis. It is also solved as a result. It is also solved using expectation maximization, because factor analysis is also solved by expectation maximization, right? So it can be solved iteratively using expectation maximization, because expectation maximization is iterative. However, one can also find a closed form solution to its expectation approach, EM approach. Okay, so it can be done. Probabilistic PCA can be done both iteratively and in a closed form solution. But factor analysis doesn't have any closed form solution. It's iterative. As you see, by making this assumption, we simplified the algorithm and we could find a closed form solution. So we sacrificed the complexity, but the solution became easier. Okay. By the way, reference 9 is probabilistic PCA in iterative approach. Reference 10 is probabilistic PCA in closed form approach. There are 2 papers on that. Okay. by restricting the noise covariance to be isotropic, the solution becomes simpler and closed form. Interesting. Okay. We can find the parameters lambda and sigma using expectation maximization. Here we don't have psi anymore because psi was sigma squared I. So only we need to find sigma. Right? Again, I don't go into the details of how to find these. It will overwhelm you. But feel free to see the tutorial paper of ours. Again, the same tutorial paper. To see the details of how we find this. Let me show you. So probabilistic PCA starts in section 4. So here are the calculations of EM. Do you see that? Here are the calculations. All of these. And as you see, where was that? So here, we have a closed form solution for, I think here. Just give me a second to remember. Yeah. Equation 63 and 64. Do you see that? These are closed form solutions for lambda and sigma. We could find it by optimization. Okay. So feel free to, if you would like, for interested students, feel free to read this tutorial paper. By the way, I have another paper which is related. I think it's worth mentioning it here. It's this. It's also worth mentioning too. Theoretical connection between local linear embedding, factor analysis, and probabilistic PCA. There is a connection between these algorithms. And again, it's related to this lecture too. So feel free to also read this paper to see how they are related to each other. Okay. Are you typing? Okay. So, by the way, let me tell you, I have forgotten to put it in the slides. Where was that? Just give me a second to find it. Why is it called probabilistic PCA? According to, as you see, section 4.3, zero noise limit. PCA is a special case of probabilistic PCA. Why? Let's see. Recall equation, the posterior, which is equation 38. What was equation 38 in this paper? Just give me a sec. Which section is it? Yeah. Do you remember this? We also had it in the slides. Okay. We also had it in the slide. So yes. So this, we already had it, equation 65. So what is it? It says that Q of Zi, the prior of Zi, is probability of Zi given X star Y according to the E step in factor analysis. And we know that probabilistic PCA is a special case of factor analysis and variational inference, right? This is the E step of variational inference. Equals, this is the Gaussian distribution. So by the way, I'm using some equations which I skipped. I said you can read. According to those equations, this is a normal distribution for this Zi given Xi. Okay, accept it from me, but for proof, read the tutorial. Okay, now consider the zero noise limit where the variance of noise goes to zero. What do I mean? Limit probability of epsilon, the prior of the noise, where sigma squared goes to zero. When the sigma squared goes to zero, what does it mean? The covariance of noise in probabilistic PCA becomes almost zero. So the noise becomes almost zero, right? Then, so as a result, the algorithm becomes non-probabilistic. Okay. So if this happens, what is the prior of epsilon? It's a Gaussian noise, Gaussian distribution with mean zero and covariance sigma squared I. When sigma squared goes to zero, As a result, it becomes the Gaussian distribution with mean 0 and limit of sigma squared goes to 0, I identity matrix, right? In this case, the uncertainty of probabilistic PCA almost disappears. It becomes non-probabilistic. In the following, we show that in zero noise limit, which we just talked about, PPCA is reduced to PCA. I think it's obvious. It becomes non-probabilistic, but it's not yet obvious why it is PCA. Okay. And this explains why PPCA is a probabilistic approach to PCA. Let's see. Consider this analysis. Limit of QZI, where sigma squared goes to 0, is the limit of probability of Zi given Xi, sigma squared goes to 0 according to the E step in the expectation maximization of variational inference, right? We saw that. And according to this equation, which I said accept it from me, but for proof, read the tutorial. According to this, according to equation 65, what happened? What was 65? Give me a sec. So as you see, equation 65 has sigma squared in them. Now I'm limiting sigma squared to 0. So these terms go away, which have sigma squared, right? So this becomes simplified. Equation 65 becomes simplified to this line. To this line. Right? Now what happens? According to this paper, Royce 1997, I have cited that in our tutorial paper. Footnote 4, okay. In linear algebra of this factor analysis and probabilistic PCA, equation 68 holds. So we accept it from Royce. By the way, who is Royce? Royce is one of the most important machine learning scientists who passed away, unfortunately. Okay, he was a student of Hinton. Okay, Royce has proposed a lot of things, such as locally linear embedding, such as t-SNE, such as probabilistic PCA. Okay. And by the way, he has proposed another thing in computer vision. He has proposed the algorithm which removes handshaking when you are taking a picture. It is being implemented in our phones nowadays, right? It is proposed by Royce. So where are we? Okay, now we are going to use this formula of Royce here. What happens? On the other hand, according to this, again, these are the two papers of probabilistic PCA as far as I remember. Tipping and Bishop. These are monsters of machine learning, Bishop and Tipping. Okay. In the year 1999, Appendix C, PCA also minimizes the reconstruction error as this. Okay. Where this is Probabilistic. Okay. We already talked about it in the previous lectures that PCA minimizes the reconstruction error. Do you remember? PCA, don't you remember? PCA could be formulated in two ways. Either it maximizes the covariance matrix, or it minimizes the covariance matrix after projection, or it minimizes the reconstruction error. Okay, so that's the thing that we have in equation 69. Instead of minimizing the reconstruction error, one may minimize the reconstruction error of the mean of the posterior, according to this, again, Appendix C. This is the minimization of reconstruction error after projection by this. Okay. According to the posterior in the zero noise limit, this is equivalent to PPCA in the zero noise limits model. Let's see. Let's see. Do you see this? You see this? Also compare it with this. So basically, this is saying that this in this minimization of reconstruction error is PCA. This also appeared in probabilistic PCA when the noise became 0. So this explains that why when in the zero noise limit probabilistic PCA, first off, it's obvious it becomes non-probabilistic algorithm. But according to this analysis, it becomes PCA. As a result, PCA is a special case of probabilistic PCA where noise is 0. Okay. Again, if it is a bit complicated, I apologize. This is probabilistic machine learning. So acknowledgement, some slides are based on our tutorial paper, Factor Analysis, Probabilistic PCA, Variational Inference, and Variational Autoencoder Tutorial and Survey. Some slides of this slide deck are inspired by teachings of deep learning course at the Carnegie Mellon University. They have a very good YouTube channel. Okay. Just on YouTube, search Carnegie Mellon University Deep Learning. Okay, we also have factor analysis in scikit-learn that you can use. Okay. And these are the references. So as you see, this is one of the probabilistic PCA papers by Tippin and Bishop. The other one is this by Sam Royce. I said there are two papers. One of them is, I don't remember which one. One of them is the iterative algorithm. The other one is the closed form algorithm. Okay. Any question? No? Let's have a break and come back at 8:35. Is it good? 8:35. Come back at 8:35. And then we'll continue with t-SNE. And after t-SNE, if we have time, we can cover UMAP. Okay. Okay. So now we continue with SNE and t-SNE. These are also important algorithms in machine learning. SNE and t-SNE, also UMAP, they are used, t-SNE and UMAP, they are nowadays mostly used for visualization of high-dimensional data, such as features of neural network and genomes, etc. So there are state-of-the-art algorithms for visualization algorithms of dimensionality reduction. Okay. A stochastic neighbor embedding, or SNE in short, it was proposed in year 2003. It is a manifold learning and dimensionality reduction method which can be used for feature extraction. Okay. You know that. What is feature extraction? You know that or no? So feature extraction, many of the algorithms that we talked about so far, many of them were feature extraction algorithm. Feature extraction algorithm is another name for dimensionality reduction. What does it mean? So we have a general name named feature engineering. It can be, it has two categories: feature selection and feature extraction. Feature selection means that we select a subset of features out of the existing features. Okay, so we drop some of the features which are redundant or not useful much. You can see both feature selection and feature extraction as reducing the number of dimensions. But whenever you say dimensionality reduction, we usually mean feature extraction. What is feature extraction? We reduce the number of dimensions, but we completely transform the features to some other features. Completely change it. Okay, for example, we have 100 dimensions features. We transform them to become, or compress them to become 20 dimensions, but these 20 dimensions are not a subset of those 100 dimensions. Completely, there is a transformation here. Okay, that's called feature extraction. We are extracting features, but we usually also, in both feature selection and feature extraction, we are reducing the number of features, right? And there are pre-processing algorithms. For more information on feature selection and feature extraction and their different algorithms, see this paper of ours. This is a very good paper, in my opinion. Feature selection and feature extraction in pattern analysis, a literature review. Okay, it explains different feature selection, feature extraction algorithms and compares them. For example, for feature selection algorithms, there are two approaches for feature selection, two broad approaches, family of methods. One of them is filter methods. The other one is wrapper methods. What are these? Assume I want to do feature selection, select a subset of features. So filter methods, they don't care about the classifiers because these are pre-processing algorithms. They don't care about what we are going to do afterwards, classification, regression, whatever, okay? They care about the relation of features to each other. And for example, again, there are several approaches for filter methods. For example, either we can calculate the mutual information or correlation between the features themselves. If two features are very correlated, what does it mean? One of them is redundant. We can drop it. One of them, right? If they are very correlated or their mutual information is large, we can drop it. What about feature and label? Assume I have the label and I have the feature. I can calculate the mutual information or correlation between feature and the label, right? If the correlation or mutual information of a feature with label is high, then I need to keep it. If it is low, I need to drop it. So there are two approaches for filter methods that I explained. Wrapper methods, they care about what we are going to use afterwards. For example, if we have a classification afterwards, then we select some of the features with maybe randomly or in a wise way, and then we see what happens with the accuracy or FS score, or if it is regression R2 score, whatever. There's features which maximize the accuracy or the measurement, right? The performance, then those are good ones. So we wrap our algorithm around the classifier or regressor afterwards, right? So those are wrapper methods. And feature extraction methods, dimensionality reduction algorithms, or feature extraction methods fall into 4 categories. And for more information, you can read our paper, Elements of Dimensionality Reduction and Manifold Learning, published by Springer. Our book. This is the book that we have written. But what are these? One of them is spectral algorithms. Three methods, categories. Spectral algorithms, probabilistic algorithms, and neural network-based algorithms. Okay. There is also Riemannian algorithms, where you can consider it as the 4th category as well. Okay, Riemannian manifolds. Anyways, spectral algorithms, they work with a geometry, and they're usually reduced to eigenvalue problem. Examples that we saw in this course, we saw a lot of feature extraction algorithms in this course. PCA, FDA, Fisher discriminant analysis, kernel PCA, kernel FDA, all of these, right? These are spectral algorithms. Local linear embedding, isomap, multidimensional scaling, all of these are spectral dimensionality reduction algorithms. Probabilistic dimensionality reduction or feature extraction, examples are, we just saw it, factor analysis, probabilistic PCA, right? Random projection, I have talked about it in this course a bit, and some other things. So another example of probabilistic feature extraction is this that I'm explaining right now. SNE, t-SNE, UMAP. These are all probabilistic dimensionality reduction algorithms. Neural network-based dimensionality reduction algorithms, such as variational autoencoder. The variational inference which I explained today can be implemented as an autoencoder. It becomes variational autoencoder. Adversarial autoencoder. Generative adversarial networks, GAN, can be implemented as an autoencoder. That becomes adversarial autoencoder. These are neural network-based dimensionality reduction algorithms. Anyways, let's go back to SNE. So, where were we? Give me a sec. Okay. So, it is a probabilistic approach. Doesn't work. What happened? Sorry. Give me a second. Technical issue. Sorry about that. Okay. It's a probabilistic approach. Okay. And it fits the data in the embedding space locally, hoping to preserve the global structure of the data. So this approach of fitting locally and thinking globally was initially proposed by locally linear embedding. Okay, there was no time in this semester for me to cover local linear embedding. I apologize for that, but feel free to see my YouTube channel for that. Also, I have tutorial paper on that. Okay, I have video on that on my YouTube channel as local linear embedding. What is that? Many of the dimensionality reduction algorithms, they are either supervised or unsupervised, right? If it is supervised, the main idea behind supervised dimensionality reduction algorithms is the idea of Fisher in the previous century. Fisher discriminant analysis. Let's decrease or minimize the intra-class variances and increase or maximize the inter-class variances, right? That was the idea of supervised dimensionality reduction algorithms. Even nowadays, triplet loss used in neural networks is having the same idea. But what about unsupervised dimensionality reduction algorithms? Its main idea is usually this sentence: locally, fitting them locally, hoping to preserve the global structure. The famous sentence is the same title of paper by Sam Royce. Fit locally and think globally. What does it mean? Fit locally means that put the points which have similar pattern. There is no label here. Pattern is important. Put the points or embed the points which are similar to each other next to each other. So after this transformation into the subspace, the data points which are closer, which have closer patterns, they need to fall close to each other. This is fitting local. If we do that, hopefully the global structure will be preserved. Did you get it? So basically, what do I mean? Assume I have these manifold. Okay, then I say that these two are close to each other, so I put them next to each other. Then these two, I put them next to each other. Then these two, I put them next to each other. If I do that, the global structure is preserved. What is the intrinsic dimensionality of these? Is 1. What is intrinsic dimensionality? What do I mean by intrinsic dimensionality? Intrinsic dimensionality. Put an ant, a small ant, on the manifold. Do you see an ant? The ant is very small and tiny, and it can't see the whole global structure. Let the ant move on the manifold. Whatever the ant senses is the intrinsic dimensionality of data. If the ant moves, it will reach here, and it sees that the manifold ends. So basically, the ant sees that it's a line. It's a line, but finite line. As a result, its intrinsic dimensionality is one-dimensional. Right? So I could unfold it using fitting local. Many of the unsupervised dimensionality reduction algorithms have this idea. t-SNE also has this idea. Okay. The idea of t-SNE is that consider every point as neighbors of the other points with some probability, where the closer points are neighbors with higher probability. What do I mean? Assume we are data points in this class. Okay. We are in the input space. Okay. Then you are closer to me, so you are my neighbor. You're also farther from me, but I still consider you as my neighbor, but less neighbor. This is larger neighbor, better neighbor. You are less neighbor to me, right? So every point considers every other point as neighbor, but with some measurement, right? The closer the 2 points are, the more neighbor that the point is for that point. The farther away, the less neighbor, right? So as a result, for every point, I can consider a probability distribution centered at that point. Consider a Gaussian distribution around me, where the mean of the distribution is exactly my head. Okay? So now everyone will be at some point in this PDF of this Gaussian distribution, probability density function. The closer you are to me, the closer you are to the mean of the distribution. So the more probability you have. As a result, we can have this distribution is the distribution for neighborhood for every point. And every point has its own Gaussian distribution centered at that point. Okay? Then t-SNE says, so we have these distributions, okay? We can also consider these distributions in the embedding space. Embedding space is lower dimensionality. So this input space has higher dimensionality, embedding space has lower dimensionality. So I have some Gaussian distributions in the input space. I assume I have some Gaussian distributions in the lower dimensional embedding space. Then what do? Let's minimize the KL divergence between these two distributions. So the distribution in the lower dimensional embedding space matches the distribution of neighborhoods in the input space. This is the main idea behind t-SNE. As you see, it's a probabilistic approach. Do you see the beauty? Right? So preserve the probability of neighborhoods. There exist some other similar probabilities, probabilistic dimensional reduction methods, such as neighborhood component analysis, NCA, deep NCA, proxy NCA. I have provided the references for you. So as I said, t-SNE uses Gaussian distribution, okay, for neighbors. But later, someone said, let's change. Let me explain this part a bit later. Okay, I skipped this part for now. Let me first explain t-SNE. The goal of t-SNE is to embed the high dimensional data x1 to xn into the lower dimensional data y1 to yn. Here y is not labeled. Here y means embedding, lower dimensional embedding. Okay, which is p dimension, where p is much less than d. Okay, as a result, t-SNE is good for visualization because p can be two-dimensional plot, right? So for data visualization, we have p either 2 or 3. So consider t-SNE. So in t-SNE, we use Gaussian distribution in the input space. Consider this. This is the probability density function of the you tell me, Gaussian distribution with mean 0, right? And d here stands for distance. Okay. Because why is it the mean 0? Why is it mean 0? Because I have distance 0 from myself, and whoever is these x's are the distances from me, right? So mean is 0 and the random variable is the distance. Okay, and now we use this, but there is a problem. First off, let me use only this part. Ignore this constant normalization factor. Okay, but if I do that, there will be a problem. It will not be a probability anymore because probability needs to be between 0 and 1 and sum to 1. What should we do? We always do that in machine learning. We have done it a lot. We use softmax form, right? So we divide these by the summation of them. In this case, this softmax form, they will sum to 1. They will be between 0 and 1. Then they will behave like Gaussian distribution because this is in Gaussian distribution, right? Agree? Okay. So dij, by the way, here you can also ignore sigma in the softmax because they still sum to 1 for here, for this one. No, sorry. Dij has sigma in it. I apologize. So dij squared is defined as this, which is used here. Dij squared is the distance between xi. What is this numerator? The squared Euclidean distance between xi and xj. But I have this normalization over 2 sigma I squared because of this in the PDF of distribution. PDF of Gaussian distribution. So, by the way, this sigma I squared is the variance which can be which we consider for the Gaussian distribution. It can be set to a fixed number or determined by binary search, okay, to make the entropy of distribution to some specific value. Okay. I think you can simply use a fixed value as well, but they usually in the literature they usually use binary search for that. Okay. Anyways, now t-SNE uses the Gaussian distribution again in the embedding space. So Qij, the previous one was Pij. This is Qij. Okay. What is this? Qij, the distribution for point yi to take yj as its neighbor. What was Pij? Pij, the probability that point xi takes xj as its input. Okay, but qij is the same, but in the embedding space. The probability that point yi takes yj as its neighbor in the embedding space. Okay, again, softmax form, and it is a scalar. Zij is defined as the squared Euclidean distance between yn and yj. Why don't I use any sigma I here? Because I am putting the points in the embedding space. Okay, so the variance is in my control, but in the input space, the variance was not in my input control. The variance, the data was given to me in the input space. So I need to consider that sigma I, the densities of different clusters. Here, I am putting the points in the embedding space initially randomly, right? So I don't need to have any sigma in the embedding space. It kind of is absorbed into yi and yj. Okay, so in other words, sigma I squared can be set to half for in the embedding space. Okay, now what should we do? We have two distributions. We want to make one distribution similar to the other one, minimize the KL divergence between them. So this is a KL divergence between P and Q. P in the input space, Q in the embedding space. According to the definition of KL divergence, it is discrete, right? Points, discrete. So we use discrete KL divergence. This summation is over the points, but this summation is for the definition of KL divergence. Okay, as you see, we have nested loop because we have ij. For every I have a bunch of j's, right? And then what happens? The gradient of C1 is this. So this is C1, cost 1, with respect to yi. What should we do? So we want to minimize this with respect to, you tell me, yi's, right? y1 to yn. Because what? The points in the embedding space are in my hand, right? They're my optimization variables. So of course, I need to take derivative with respect to my optimization variables, and then, for example, set it to 0. Of course, I can't find the closed form solution, so I need to do it iteratively using first order optimization gradient descent. I use gradient descent using this gradient. Okay, did you get it? Did you get it? For proof of this, refer to our tutorial paper. I think I proved the formula for t-SNE as far as I remember. Okay, for SNE, I don't prove it. For t-SNE, I prove it for you. Okay, but I have, if you want to see the proof of this, see our tutorial paper. The stochastic neighbor embedding with Gaussian and student t-distribution tutorial and survey, or our textbook. By the way, this was proposed by SNE was proposed by Hinton and Sam Royce. Okay, they didn't provide the proof in their paper. They said it's complicated. Okay, but I could figure it out based on, inspired by the proof of t-SNE. I figured it out and I have provided that in the tutorial paper. You can read it. Okay. So the update, we use gradient descent because setting the gradient to 0 doesn't give us a closed form solution. Then what happens? I can use one step of, so this is one step of gradient descent, but there is a but. So only this is the gradient, is a step used in the gradient descent where eta is the learning rate. Okay, but I'm also adding this term. What is this term? Did I talk about it in this course? I don't remember. This is the momentum. Did I talk about momentum? So I have talked about it in my deep learning course. Okay, what is this? Delta I, my current delta I is my gradient step plus my previous delta Y in the previous iteration with some weight alpha. Why am I doing that? Please take a look at this. This is important, guys. Assume by gradient descent, I'm moving to this. So it becomes like this. Maybe my cost is complicated, so I go like this. Okay. using gradient descent. But if I apply gradient descent with momentum, it becomes a smoother. So I will have less oscillation. Why? So there are two reasons. First reason, intuitively. When you add a log of history, you try to follow your history. So you don't want to deviate from your history a lot. This is intuition. Okay? Now mathematical proof. What was that? This is minus eta derivative of f with respect to x. What is this? Minus eta derivative of f with respect to x plus alpha previous delta. Previous delta. Right? Okay, let's see. Assume this is my minus eta derivative of f with respect to x. Assume my previous, apparently my previous delta was like this, right? Right? Now I'm starting from here. So I should consider this vector as starting from here. This is my previous delta. Linear combination of these two becomes this. As you see, it reduced the oscillation. It moved this to here, pulled it to here. This is the mathematical proof. Okay, so momentum reduces the oscillation. Gradient this. Okay, and alpha t is the momentum term, the momentum parameter. Okay, the larger the alpha, the more we care about the previous history. So initially, alpha is less. We care more about gradient step. Then after some time, we increase alpha. Okay, not to oscillate around the solution a lot. And the eta is the learning rate, as I said. They set it to 0.1. Also, in the SNE paper, they add some Gaussian noise random jitter to the solution in the first iterations before going to the next iteration. Why do they do that? They wanna avoid local optimum solutions. They wanna explore more rather than exploit initially. Initially, they wanna explore. Gradually, then they want to exploit. Okay? Did you get it? So now symmetric SNE. Symmetric SNE was proposed in 2008 in the same paper as t-SNE. Okay. What is it? We consider a Gaussian distribution around every point xi. So this is, do you remember this? Okay. Where the ij is this, but there is one thing which you should note. Just remember, let me remember. Do you remember Pij in regular SNE? It was this. Compare these two. Equation 10 and this equation, which was equation 2. The difference is in the denominator, the summation. In equation 10, it is summation k over k not equal to L dkl. Here, I have summation over k not equal to I dik. Okay, so now change I here. Assume this is ij, I change it to ji. The denominator will change in the regular SNE. As a result, Pij will not be equal to Pji, so it's not symmetric. But if we want to make Pij equal to Pji, then we need to let the denominator to be the same for all of them. This is what they did. I think it makes sense to make it symmetric. Why? Because if you are very close to me, if you are my neighbor, I should also be your neighbor. Yeah, with the same value, amount of probability. This is the reason. Okay. So, but there is a problem here. If we use this for symmetric SNE, there is a problem. And what is that? A problem happens with outliers. Because this is considering all of the pairs. And if we have an outlier, what happens? It becomes extremely small. If point xi is an outlier, pij becomes extremely small. Do you know why? Because dij, consider calculation of pij for an outlier. Let xi be an outlier. Then dij becomes very large. Because xj is not outlier, xi is an outlier. So dij becomes very large. Minus dij squared becomes very small. E to the power minus dij squared becomes very small. The numerator becomes very small. Right? But the denominator is the same for everyone. Right? It's fixed for every point. Numerator will be very small for outlier. However, if we use equation 2, the regular SNE, what happens? This becomes a small, too small. The denominator for an outlier will also be small. Right? As a result, what happens? You tell me. So for outlier, pij doesn't become very small for the regular SNE. But for this that we just proposed, the probability for an outlier becomes too small. And we don't want to have a very too tiny value in computer for calculations, right? As a result, we don't use this. Rather, we use this, but for this to be symmetric, we say P. So let this be denoted by Pj given I, and then we say Pi given j plus Pj given I over 2 or over 2 times n, right? This is the symmetric Pij. In this case, it will not be too small for outliers, okay? That's one thing that we can use. Qij, we can use this. Again, this is symmetric because of k not equal to L. But why doesn't the problem of outliers happen for Qij? For Pij, it had an issue for outliers. For Qij, I'm saying that I use this without having any issue. Why? Because I am putting the points in the embedded space. So I don't put any outlier in the embedded space. Remember, right? It's in my control. Okay. So we can use this Qij. Again, this is scale divergence between Pi and Qi that we just defined for symmetric SNE. The formula of gradient or derivative will change. Okay. Again, for proof of this, I have provided the proof of this also in our tutorial paper. Feel free to read this tutorial paper for the proof of this equation 17 as well. Again, we use gradient descent. Okay, so far clear? Now let's talk about t-SNEs. t-SNE. So in SNE, there was a problem. Consider this just without looking at this. Assume I want to fit 10 people in this class. It's possible. 10 people come and sit. Now assume I want to fit 1 million people in this class. How can I do that? Assume this room is a magical room where you can move the walls. What do? So you expand the room, right? Expand the room, make the room bigger, larger. Enlarge the room, right? To be able to fit 1 million people into this classroom, right? Now come to the world of dimensionality reduction. Here, the number of people in our example is like the amount of information. In my high dimension, I have a lot of information, like 1 million people. In 2 dimensions, 3 dimensions for visualization, the dimensionality is very low. P is much less than D. It's like we want to fit 1 million people in a small classroom. It doesn't fit. We will have a lot of loss of information, right? So that's the issue with SNE. Then someone named Van der Mateen, who is now a professor in Europe. He used to be a student of Hinton, okay, in U Toronto. What did they do? They said they had this simple idea: let's enlarge the room. So SNE used Gaussian distribution in the input space, also used Gaussian distribution in the embedding space. They said, why? Who says that we should use the same distributions in the input and embedding space? Let's use the Gaussian distribution in the input space, but use another distribution in the embedding space where that distribution has larger tails, is enlarged. So if the Gaussian distribution is like this, let's use some distribution which goes like this. It's enlarged. So it can fit more information in the embedding space, because embedding space is small in terms of dimensionality. What's distribution? So if it is Gaussian, do you know any distribution which behaves like this? Heavier tails than Gaussian distribution. You know, uniform is like this, right? But this one is called a student t distribution. Okay. A special case of a student t distribution is a standard Cauchy distribution. How was it written? I think it was spelled like this. A special case. Okay. So they said, let's use a student t distribution. In their paper, they used the special case, Cauchy distribution. Okay. In the embedding space. This simple idea improved SNE a lot, that it became a journal paper. Okay. So that's the idea that I was talking about. So we have the room. Let's enlarge it. Enlarge the room. Use a distribution with heavier tails. This problem that I explained is called crowding problem, because we have a crowd, right? So as a result, let's use the Gaussian distribution as before in the input space, but in the embedding space, we use this. What is this? Zij is like that. We defined it as a squared Euclidean distance of yi and yj, right, as before. But I'm not using, this is not a Gaussian distribution anymore. It's not a softmax form. It is this over summation of all of them. Still, it behaves like a probability. They sum to 1. They are between 0 and 1, but it's not Gaussian distribution. This is in the form of this. Do you see that? Because I can write it as some scalar, which I don't care right now, 1 plus z squared to the power of -1. Drop this part. Of course, it will not sum to 1. So divided by summation of all of them. So they sum to 1. This is, what is this? The standard Cauchy distribution, which is a special case of a student t distribution. Uniform is because the distribution should have a mode, one mode around the point itself, because the point is its own neighbor with the highest probability. The further you go, the probability of being neighbor should decrease, but the uniform distribution never decreases. If you use uniform distribution, it means that you are as close to me as him, but you have different distances from me. He's more neighbor to me than you, right? Because you're farther away from me. So we shouldn't use Gaussian. The mode should be on me only, right? That's why I'm saying that the original, oh, by the way, that's why they named it t-SNE, T for a student t distribution. By the way, why do they call it a student t distribution? Do you know that? Because the author of the paper in proposing this distribution named himself a student as his nickname. He didn't use his original name. Okay. And I think he named that distribution T distribution, I guess. As a result, they named it student T distribution. Okay. Although that author was not a student. I don't know why he named himself a student. Okay. Anyways, that's why they call it t-SNE, first off. But I think original SNE can also be named Cauchy SNE. This is original T's, right? Because they use Cauchy distribution. If the student T is, we can also use general degrees of freedom of a student T distribution. So this is a student T distribution, the PDF of a student T distribution. If you set, so delta here is a degrees of freedom. So this distribution has a parameter named degrees of freedom, okay? For some specific degree of freedom, maybe 0 or 1, I don't remember, it becomes Cauchy distribution, okay? But you can use the general degrees of freedom for t-SNE. Then Qij becomes this with degree delta, okay? Yes, first degree of freedom becomes Cauchy distribution, and it has the heaviest tail, right? When you increase the degrees of freedom, the tail becomes less heavy. If you limit delta to be infinite, it will converge to Gaussian distribution, I think, as far as I remember. Okay. So far clear? Okay. That's why they use Cauchy distribution, because they wanted the heaviest tail. Okay. By the way, t-SNE with general degrees of freedom has also been proposed. Reference 15. So what do they, do you remember I said they use Gaussian distribution in the input space like SNE, but they use symmetric Gaussian distribution in the input space. So again, they define this and they use this, do you remember, for symmetric Pij. So far clear? And they also find this sigma I using binary search as before, okay? So Qij, they use the Cauchy distribution. This simple change significantly improved the performance of SNE. Sometimes ideas are simple, but they have great value. So again, we have the scale divergence between them, C3, cos 3, and its derivative becomes this, its gradient, and we use gradient descent with maybe with momentum or without momentum, doesn't matter, to find yi. We do it until convergence of all of the y's, right? So what is the termination criterion? When the yi's, the embeddings don't change significantly, okay? All of them, okay? Now I'm gonna prove to you these gradients in a few slides, okay? By the way, Pii and Qii in this formula, we assume they are 0, okay? We assume. So I don't say Pii is 1 or something. I assume it's 0 in this formula, okay? Let's prove it. Proof. I think we have 10 slides for proving, several slides, okay? It's a bit long. So Rij, let it be defined to be Zij squared, but which was the squared Euclidean distance between yi and yj, okay? Now you tell me, if I change yi, what happens? What does it change? It will change both Zij and Zji, right? Agreed? Because Zij and Zji, they both are the Euclidean, squared Euclidean distance between yi and yj. So as a result, I use chain rule in derivative. Derivative of C3 with respect to yi, derivative of a scalar with respect to a vector becomes a vector, right? Then what is it? It is derivative of C3 with respect to Rij times derivative of Rij with respect to yi, also plus derivative of C3 with respect to Rji times derivative of Rji with respect to yi, because it has effect on both, right? Both on both Rij and Rji. And also I need to sum over j, right? Because I should see what changing yi might change any of the yj's. Also, what according to this rij is defined as this according to equation 28. As a result, this derivative becomes 2yi minus yj, right? It's quadratic with respect to yi. Rji also is equal to rij. So as a result, its derivative is the same, right? Therefore, replace these here and you will get this. This is therefore in mathematics, right? You will get this. The cost function, let's rewrite it. It was this, KL divergence between P and Q, right? So this is my notation. Rather than writing two summations, I summarize them in one summation. What I mean two summations. K not equal to L means sum over both K and L, but not equal to each other. Okay. Also, PKL, so I write logarithm of A over B as logarithm of A minus logarithm of B. Okay. The first term doesn't have any KQL, right? Also, so it's a constant for KQL with respect to KQL. As a result, it's also a constant with respect to RKL. Right? So what happened? Sorry. Yeah, sometimes my device gets tired. Okay. So it now what am I doing? I'm gonna calculate the derivative of C3 with respect to Rij because I have it here, right? Rij or RKL, whatever. So with Rij, what is it? Squared Euclidean distance between the embeddings, right? Right? This first term doesn't have any embedding in it. It's only related to the input space. So it's constant. We drop it in the derivative. Agreed? Its derivative becomes 0. So I only have this term. So its derivative, so minus is here. And I have this summation here. PKL is the constant with respect to that. It becomes here. So I will have derivative of logarithm. It becomes the derivative of logarithm of QKL with respect to Rij. What is Qij? It was this. Do you remember? Equation 24, the Cauchy distribution. As a result, QKL is this, right? Rather than Z squared, I use R because of what we defined it here. Equation 20. And let's denote the denominator to be beta. Okay. So far clear? To be beta, and again, I replace this with R. Z squared with R. So far clear? Okay. So I'm repeating what we had. We had this. We also had this. We also defined the denominator to be this. Okay. Now you tell me. So here I have logarithm of QKL. Can I write it as logarithm of QKL plus something minus that thing? Yes. Now let me combine these two. So it becomes logarithm of QKL beta minus logarithm of beta. So I replace this with what I found here. I'll get this. Right? Now I know the derivative is a linear operator. So I can break down as fraction to these. Now here I do chain rule. derivative of logarithm becomes 1 over that, then derivative of this part, the argument. Also here, again, chain rule. Derivative of the logarithm becomes 1 over beta, then the derivative of argument with respect to Rij. Okay, so far clear. What is QK? Now I think you understand why Hinton said it is complicated and didn't even mention it in his paper. This is t-SNE and proof of SNE is similar. Okay. QKL beta is the what? By the way, you might be wondering, why is it useful for us? This is teaching you techniques. I have learned a lot of techniques from this proof. I propose an algorithm where I use the techniques used in this proof for proving my own derivatives. If you don't believe me, read my paper QQE. I have a paper named quantile embedding. Okay, go and read that. Its derivative, its proof is very similar to the proof of SNE and t-SNE. So I'm teaching you techniques. Okay. So QKL beta. So QKL is this. We already talked about it. And beta is this. So QKL is this, and beta is this. As a result, they cancel each other, so we will have only numerator. Obviously, because beta was a denominator of QKL. So what happens? Let me think. Here I have QKL beta, which I just saw, it becomes this. As a result, I replace QKL beta with this, and the rest as before. Okay, so we have this. So this is what we found. Okay, now let's calculate this. Okay, it is non-zero for k equals I and L equals J. Why? Because here I have RKL, here I have Rij. When I is K, J is L, this is Rij, this is also with respect to Rij, this will be non-zero. All of R combinations are constant with respect to Rij. If it, for example, if it is R32, R56 is a constant with respect to R32. Only R32 is not constant with respect to R32. Right? So K equals I, L equals J. So I replace this RKL with Rij. The rest are zero, their derivative. Okay? Then what is the derivative of this? The formula in high school, the derivative of power is this, right? The derivative of beta with respect to Rij. Beta was this. Its derivative with respect to Rij. Okay. Then what happens? Again, it's summing over different permutations of M and F, where M is not equal to F. The only thing which is not constant with respect to Rij is when M is I and F is J. So I only have this, and the summation goes away, right? Again, the formula of derivative of power in the high school. So we just calculated these two. Let's replace these here, and we'll get this. Sorry, yes. Let me explain. It needs some more explanation. So first off, so this, do you see this? Is here. So far clear? And this term, I said one of them is this, which is this minus is here, and this is here. So far clear? And the rest I said is zero. Did you not get it? Did you get it? Did you all get it? Okay. The rest is zero. What about this? So 1 over beta is here. This, we calculated, which was here, this one. But it had minus here, so minus becomes here. Sorry, note that. Minus times minus becomes positive, times minus becomes negative again. Okay? This minus also appeared here, but the parenthesis ends here. Don't get confused. Here I have 3 minuses. 1, 2, 3 becomes negative. Okay? Okay, you need to be careful about signs. Where were we? Let me clean this part a bit. So, yes. Okay, do you see a slight difference between these two? I want you to notice that. Here, this is one term. The summation of it is behind it, right? Behind it is here. And I said only when k equals I and L equals J, I have this, the rest will be 0. That's why I said I have this term and the rest are 0. And the summation went away. This is the summation that I opened. Okay? Here, inside beta, I have the summation. And it already filters one of them. So that's why I have put it outside of this big parenthesis. Okay. Then, where were we? Okay. Just give me a second. Here, interestingly, this doesn't have any K and L in it. Can come out of the summation over K and L, right? Then I will have summation of PKL over K and L. Basically, it means that summation of all of the probabilities. It is 1. Right? So far, so as a result, it becomes this, and this summation becomes 1. So times 1 is that thing. And the rest, this is also the rest. So far clear? I'm simplifying it step by step. Then, what happens? Let me remember. Oh, okay. So let's factor out. Do you see this term? We also have it here. Right? Do you see these two? Do you see that? Also, I factor it out here. This times this becomes this, right? Didn't get it? No. Ben to the power minus 2. Ben to the power minus 2. I factor it out. It becomes Ben to the power minus 2. I write it as Ben to the power minus 1 times Ben to the power minus 1. Okay. I named this Ben. Okay. And then I also have 1 over beta. 1 over beta, I factor it out. 1 over beta. So far clear. This minus and this minus cancel each other. I will have Pij over Qij. I also have minus 1. Right? Right? The beauty of mathematics is that when you go inside, deep inside it, you will forget the real world. And as real world is usually depressing, it's also a cure for depression. It's very good because you forget everything. So now what happens? You tell me. Why did I break it down into Ben to the power minus 1, Ben to the power minus 1? Because interestingly, this part is Qij. Right? So as a result, I have this, which I repeated here. Qij times Pij over Qij becomes Pij. Right? The Qij's cancel each other. Qij times minus 1 becomes minus Qij. Agreed? Agreed? So, did you see how simplified it became? Derivative of C3 with respect to Rij. Where did we have it? It was here. It became very simplified. Right? We also have derivative of C3 with respect to Rji, which is very similarly found. We need to change the orders of the Ij. So this was what we found. As a result, derivative of C3 with respect to Rji, just change change the order of I and J. Okay? But we know that Rij and Rj are equal to each other because they were both a squared Euclidean distance of Yi and Yj. So I replace it Rji with Rij. But we also know that we use in t-SNE, we are using symmetric Pij in the input space. Do you remember? So Pji equals Pij, right? What about Qji? That's also equal to Qij, because if you see Qij, it's symmetric with respect to I and J, because it has Rij equals Rji, right? The Cauchy distribution is a symmetric one that we're using. So as a result, these two are equal to each other. What did we have? We already had it. Do you remember? Let's go back. Question 29, I guess. We already had it. Okay. So these two are, we just saw that they are both equal to this and they're equal to each other. As a result, I have this here. I'm just changing the order of multiplication. Doesn't matter. They are both a scalar, right? This is, I have 1, 2 here, but they are two equal to each other. So I will have another 2 here. 2 times 2 becomes 4. I factor it out in the summation. Summation is as before. This is as before. We just proved it. QED. QED means proof. Proof, done. Do you see that? How beautiful it was? Now, again, we use gradient descent with momentum until convergence. Interestingly, they saw that empirically. They saw that there is no need to jitter anymore for initial iterations in t-SNE. It's already robust. It's very powerful. But they need to do some other thing, some numerical hack or some heuristic thing. Okay? What is that? They saw that by experiments. They saw that it is better to multiply all Pij's by a constant such as 4 in the initial iterations. So Pij times 4. Why? Do you know why? In initial iterations. This is called early exaggeration. They are exaggerating Pij in the early iterations, right? Because they want to focus on the large Pij's, close neighbors, more in the early iterations. Do you agree that this equation 31 has more impact when Pij is large? When Pij is small, it is still multiplied by 4. But if you multiply 1 by 4, no, Pij is between 0 and 1. So if you multiply 0.0001 by 4, what happens? If you multiply 0.9 by 4, what happens? The larger value will be exaggerated more, right? What does larger Pij mean? The neighboring points in the input space. So they want to say, they want the algorithm to focus on the neighboring points first. Do you remember the famous quote? Fit locally, think globally. They're fitting locally in initial iteration. Right? Then after some initial iterations, they say, okay, now consider all of the points, all of Pij. Now with the same I mean. But initially, on focus more, still I'm considering all of the points, but focusing more on the neighboring points. Early exaggeration, by the way, is optional, not mandatory. But it's good to do it in the t-SNE. We can have general degrees of freedom for a student t-distribution in t-SNE. And that's this, right? As I told you, if degrees of freedom goes to infinity, the student t-distribution tends to Gaussian distribution, which was used in SNE. So as a result, you can see SNE as a special case of t-SNE with general degrees of freedom. Okay. So when delta is 1, degrees of freedom is 1, it is Original t-SNE, original t-SNE. If delta is infinite, it is SNE. Okay. By the way, they pronounce this different ways. Some people call it t-SNE, some people call it t-SNE. Doesn't matter. Okay. Let's see an example. They have trained t-SNE on digit data. Okay. So you can see some of the examples of these digits, 0 to 9. Interestingly, after convergence, you see that they have made some clusters. Why does this? Why is it happening? Because initially, if you plot, so because this is after many iterations. Initially, in the first iterations, it's a crap. It's shuffled. The points are shuffled, right? But by gradient descent, you're pushing the similar digits toward each other, the similar patterns toward each other. So they are pushed toward each other until each class becomes a cluster. Right? Agree? Did you understand? So it's very interesting. And another interesting thing is that these dimensionality reduction algorithms, they also usually not only they put the similar patterns of the same classes, if we have some labels next to each other, but even the clusters which are closer to each other, they have similar patterns, more similar patterns. What do I mean? Let me think. For example, this is 0. This is 9. 0 and 9 are similar to each other. Don't you agree? This is 0. This is 9. 9 only has additional this tail. That's why 0 and 9 have been embedded closer to each other. Not only the zeros are next to each other, embedded next to each other, but also the relation of clusters matters. Right? But for example, let me 3 is here. 3 and 0 have a lot of difference. That's why they have been embedded apart from each other. Right? Here we have 1. Is 0 and 1 close to each other? Not very much. That's why we have also 1 here, but a bit yet. Yes. Why? Because 0, make it thin. Make it thin, becomes 1. Right? What about 2 here? 2, 2, 2, 2, 1. Right? Interesting. Acknowledgement. But some slides are based on our tutorial paper, a stochastic neighbor embedding with Gaussian and the student t-distributions, tutorial and survey. We can also, it has appeared as a chapter of our book, Elements of Dimensionality Reduction and Manifold Learning as well. For more information on SNE and t-SNE, refer to our tutorial paper, as I said, because we have, I have explained more things, additional things in that tutorial paper. We didn't cover everything here. If, for example, discussion on degrees of freedom. You can see the discussion in the tutorial paper. Some slides of this slide deck are inspired by teachings of Professor Ali Qudsi at the University of Waterloo. By the way, some of the proofs which we skipped can be found in our tutorial paper. The code of SNE and t-SNE, I have coded them manually myself. You can see it in my GitHub page. And t-SNE also exists in scikit-learn. You can use it. Okay. By the way, there are some techniques to accelerate t-SNE, like some tree algorithms. We didn't cover that as well. Okay. And these are the references. So this is the main scholar in t-SNE, Vander Matin. I think he's in Poland. I don't remember, but I think he's now a professor in Poland. Previously, he was a student of Hinton in Canada. Okay, as you see, Hinton. So visualizing data using t-SNE. This is a paper which was published in Journal of Machine Learning Research. I guess their referee, their judge, was Sam Royce. as far as I remember. Published in 2008. And these are the rest of the references. We don't have time to cover other things, but let me tell you briefly what other things exist. For example, one of them is UMAP. What is UMAP? Very, very briefly, let me tell you. UMAP is short for Uniform Manifold Approximation and Projection. Is another famous technique, a state-of-the-art technique for visualization of high-dimensional data in lower dimensions. So UMAP and t-SNE are both state-of-the-art methods. They are competing with each other nowadays for visualization. They are also used for visualizing the features of neural network. So you have a neural network, you can plot the features and see how the features are working. Also, for a specific input, what are the features of that input in this layer of the neural network? For example, you train a neural network, and in the one to the last layer of neural network, you want to see how the points are separated from each other, right? So you can use t-SNE or UMAP. UMAP basically also all of them have the same idea. UMAP has some forces, repulsive forces and attractive forces. So what is it saying? Let me tell you this. Give me a sec. Here is our tutorial paper on UMAP. Uniform Manifold Approximation and Projection, UMAP and its variants, tutorial and server. Also appeared as a chapter of our book. So here is the cost function that we minimize in UMAP. What is it doing? You tell me. Equation 6, I mean. This term, by the way, you can analyze UMAP in various ways. If you read the original UMAP paper, you might not understand it completely because it is explaining by algebraic topology, category theory, pure mathematics, okay? Because the authors were mathematicians. But they also explain it in another way, which I also explain it right now. What is the first term? By the way, I have explained in both machine learning way and pure math way. Both sections exist in this tutorial paper, okay? The first term, so PI, by the way, PIJ is the probabilities of neighborhoods in the input space, QIJ, probability of neighborhoods in the embedding space, similar to what we had in t-SNE, right? And what is this? When you minimize this, is similar to the KL divergence between PIJ and QIJ, right? Or kind of cross entropy, because cross entropy and KL divergence have relations. And also, what about this? That's why they call it fuzzy cross entropy. What about this? This is a KL divergence of cross entropy between 1 minus PIJ and 1 minus QIJ. When the 2 points are close to each other, PIJ is large, right? So the first term gets important because 1 minus PIJ becomes very small. So the first term gets important, and we are minimizing that. What do I mean? I want QIJ to be similar to PIJ when XI and XJ are neighbors of each other. So this is attractive force. I attract their embeddings to each other. What about the second term? When PIJ is small, it means that QI, XI, and XJ are far away from each other in terms of pattern. So PIJ gets small. So the first term goes away almost. But the second term is 1 minus PIJ, which becomes large, right? Then I'm making 1 minus QIJ similar to 1 minus PIJ. What does it mean? It means that this is a repulsive force. What do I mean? When 2 points are far away from each other in the input space, let them be also far away from each other in the embedding space. Because when they are far in the input, 1 minus PIJ gets large. Let the 1 minus QIJ also be large in the embedding space. So let them be far away from each other in the embedding space as well. So first term takes care of neighbor points. The second term takes care of distant points, dissimilar points. Similar points should also be embedded similarly in the embedding space. Dissimilar points should also be embedded dissimilarly in the embedding space. Do you see? Now we have addition of these two in the last function. This is UMAP. You see how it is working? Interesting. And UMAP has its own variants. It has supervised version, unsupervised version, but the unsupervised version is the most famous one used now. And also its library exists in Python. It's not in scikit-learn, but it is available in PEEP and Anaconda. In this, it's famous. Yes, I think we concluded the lecture and also this semester. So there were several things that I didn't have enough time to cover, such as local linear embedding, isomap, multidimensional scaling, and maybe hidden Markov model. So I apologize for that. There was no time, but feel free to read my tutorial papers and watch my YouTube videos. And if you have any questions on them, feel free to reach out to me. But we covered a lot of things. We covered classification algorithms, regression algorithms, many of the dimensionality reduction algorithms, right? And many of the preliminaries required things. I hope you learned enough. How is it? The whole course? No, really. Yeah. Honestly.
I just kind of revisiting everything.
Yeah. Okay. So I'm happy that you liked it. So next session we'll have presentations. Please prepare your presentation and your results analysis. Also try to explain the results, analyze them, compare them. Right. Thank you.
Thank you very much.
Thank you. Thank you. Thank you.